Okay, so this should be a short lecture, we'll see, about sigma and pi bonds specifically, and also how a hybrid bond can in fact be part of a combination. You can have hybrid bonds and normal pi bonds, and you'll see why. I also want to play the video I forgot to play at the last lecture. So let's see, going to PowerPoint. So double and triple bonds, this is where pi bonds come into play. A sigma bond, let me see, what's this? All right. A sigma bond is a single bond, and you always start with a sigma. So pi is double or triple bond, and it involves the p or d orbitals. But your sigma, which can involve any combination of orbitals, is your single bond. It is the first bond. So always remember that. And sigma is single, Si, right? Is single bond. So remember the Si. Okay. So what is a sigma bond? A sigma bond is an overlap along, we just call it the x-axis. It's just a terminology we all start. The x-axis is our horizontal axis with our standard of measurement and space. So it's along the x-axis. Again, if the orbitals are this way, it would be along the y-axis, but that's just a terminology. So it's along the same axis though, so that the nuclei are lined up. So they have to be lined up properly in order to form this overlap, which creates the sigma bond. So you have the nuclei line up. Here are your nuclei here for the P's. This is hybrid. And you have overlap, and the amount of overlap and orientation lead to the strength of the bond. Now remember, if you have you have polarity, you're going to have an irregularly shaped bond, but that's a bit of a nuance. We're going to keep this simple right now and just talk about the overlap. So you can have two S's, two P's, two hybrid. You can have an S and a P, if you remember that from a previous slide. Where is that? So you can have an S and a P. You can have a D and a D as long as they are aligned and they overlap. That is the sigma bond. And the important thing about the sigma is that the electron density is between and around the two nuclei. The electrons are being attracted to the protons in each of these nuclei. And so they are between. This is important because the pi bond is not between the nuclei. It is above and below. All right, so your first bond is your sigma. A sigma bond allows for free rotation along the axis. So my atom I have here and here, they can rotate. All right, they can freely rotate around this single bond. There's nothing holding it in place. And again, that's important because a pi bond cannot do that. So two important differences right there. A sigma bond, you have to have overlap, direct overlap along an axis, and the electron density is in between the two and around the two nuclei. So it's between and it's also directly around it. Your pi bond, they have to be parallel, not overlap, and the density is above and below the axis of the nuclei of the sigma bond. And a pi bond does not allow for free rotation, a sigma bond does. So that allows for different conformations. When you have this rotation, you can get this bend, right? These can twist and turn, and you can just get these different conformations. Now, with a pi bond, this, as long as this is aligned with this, if this were a pi bond, well, never mind, that's immaterial. This can rotate freely, and so this atom can be lined up with this one or around, it doesn't matter. You have free rotation, and it allows it to be bendy and form all kinds of conformations, even though it's the same molecule. It's not an isomer, because of the sigma bonds, it twists and turns and swirls as long as this nucleus is in line with this nucleus. That's all that matters. There's my electron density. Everything else is free to play. It's part of the degrees of freedom. So you have rotational freedom along a sigma. However, with the pi bonds, you do not. Pi bonds are P or D. We're not going to go into F. But you have the lobes above and below. They are parallel. And the overlap is above and below. Very important. This is a single pi bond. So you have your two nuclei, the little dots down here. Your sigma's in down here. Because a pi bond, I'm sorry, a p orbital, this is a single p orbital. The electron goes up, spends its time in both nodes. Same with this one over here. So you have two orbitals, just like you have two orbitals that create the sigma, you have two orbitals that create the pi. However, they happen to have electron density both above and below the sigma axis, not in between. Remember, there's a node there. And this is where the electron's wave character comes into play. So the electrons spend their time above and below. That is a single pi bond. So this would be an example of a double bond because the single bond is the sigma, right? Sigma, single. The second bond is this pi bond above and below. The other bond, if you have a triple bond, where's that picture? Let's go all the way back up here. Your triple bond is, so in that picture I just showed you, we had along what I'm going to call the x-axis, our sigma, and then parallel p orbitals along the y-axis, above and below, that's these guys. Our third, our triple bond, is the z, the p orbital along the z-axis. So it's coming out of the plane and behind it. And it is going to have overlap in front of and behind the sigma bond. So this is a triple bond. You have the sigma with these, this is an sp orbital, hybrid. Your first double bond, these have to be parallel, and then your pz's are parallel. And so they create overlap in front of and behind. And you can see why these cannot be rotated. There is no rotation, free rotation around a pi bond, because as soon as you rotate one of the atoms, see, these atoms can rotate all they want, but in a pi bond, you have to have these aligned, and not these atoms, but the orbitals for this atom and this atom. The p orbital has got to be parallel. They've got to be perfectly aligned with each other in order for this overlap to happen. So you can't rotate, because as soon as you rotate, you break that parallel. I think this picture down here shows it. See, as soon as you rotate, it's no longer parallel. You are no longer sharing the electrons, and so you've broken the bond. So pi bonds are fixed. They do not rotate. They are the second or third bonds that form. You start with the sigma. And they can be formed from unhybridized orbitals. In other words, your sigma is going to be, if you have hybridization, they form the sigma bond. You can still have p orbitals or d orbitals that are not involved in that hybridization that can be involved in your double and triple bonds. So here is an example. Let me enlarge this. I have ethene, C2H4. So I'm going to go to the whiteboard. Why don't you draw this? So ethene, C2H4. Well, if I have a carbon and a carbon, there's my C2, 2 H's on each carbon. So obviously I have a double bond here in order to fit my Lewis structure. So this double bond means this is, one of these is a sigma and one of these is a pi. So first let's talk about the hybridization for the sigma. Each carbon is the same, so I'll just pick one. What is the AXE of this? This carbon stands for A. X is the number of connections. There are 3 connections. There are no E's. There are no unshared electrons. So this is an electron group of 3. What is 3? It's the trigonal planar. And sure enough, if you just look at this shape, that is trigonal planar. Okay, if it's 3, I need an SP designation that adds up to 3. So I start with S. You can have one S orbital. I need more, so I'm going to go to P. 1 plus, how many P's do I need? I need 2. So this is an sp2. So that sigma, and that sigma are all sp2 hybridized. Because this carbon has 3 single bonds that are of equal energy and that are sp3, 30% or 1/3 S, 2/3 P. And there are the 3 electrons from carbon that get shared by, this one makes the bond with hydrogen, so the hydrogen's electron, this one is the other hydrogen, and this one makes bond with the carbon. So there are your 3 hybridized bonds on that carbon, and it would be the same thing for the other carbon. All right, so what do we have left though for this pi bond? I'm going to erase the name so I can have room. So this carbon, some more colors, has, and it's the hybridized, so it's an sp3. So, you know, we're going to make the big fat. Okay, so I'm not very good at drawing. That's a sigma sp3. And it's doing the same thing out here. And there's my hydrogen S. That's an sp3, that's a sigma. And then I have, this is supposed to be some kind of bulbous looking, and there's my hydrogen, 1s. This is also an sp3, and that's my sigma. Okay, the same for both carbons. So that accounted for 2 of the, sorry, that should be sp2. 2 of the p's, but carbon has 3 p orbitals. Any atom that has a p orbital has 3 of them, because that's just the way quantum electrons work. So it has 1 more p orbital that's not being used in this hybridized bonding. So we're going to put them up here. There's one, there's the other one, right? Because 2 of the p orbitals, because remember, carbon is 1s2, 2s2, 2p, where's my periodic table? 2. These orbitals are the ones that are used. I'm running out of room. So we have the 2s and the 2p. This is the non-hybridized. This is where we started from with carbon. And it's 2s2, 2p2, right? And we ended up with the hybridized 3 orbitals. But you still have okay, sorry. So we have our 3 hybrid orbitals. We fill it with 3 of the electrons. We still have 1 p orbital that's not used, and there's an electron in there. because we have 4 total. So let's say we used these orbitals for my hybridization, because we have 3 electrons, 3 orbitals for our hybridization. Okay, so I have these, each carbon has a p orbital that's not being used, and it's an irregular orientation, and so that's my overlap. And that is my pi bond right here. There's my sigma, right? I should have done that in a different color. So this is above and below the nuclei. Your sigma, the electrons are shared in between, right in here, and a little bit around. The pi bond is above and below only. Now, one thing very important, these p orbitals do not bend toward each other. They do not do this, okay, to do the overlap. They do not overlap by touching. They overlap by being parallel, and that enables the sharing to occur. And we'll just stick with that right now. To go any further, we'll be going into another level of chemistry. So just recognize that when they are perfectly parallel and you have the sigma bond going on, the electrons are able to share in these orbitals, which are still associated with that nucleus. Okay, back to the slides. So this is how you can have a combination of hybrid bonds and non-hybrid, bonding with uninvolved. And you say the bonding is your sigma, your doubles are incorporating non-hybridized bonds. Come on. Okay, so let's look at this example. You have formaldehyde. Oh, wait, it jumped me to the rest. Come on. There we go. So formaldehyde, which give me the, it's a CH2OO. This oxygen is also involved, has hybridized orbitals. One of them is involved in bonding. The other 2 are not. They're the unshared pair. But remember, we are starting with the Vesper conformation. So this oxygen, in fact, does have a Vesper conformation. We generally only talk about it with the central atoms. But because it has these orbitals, these unshared pairs, and it does give you a trigonal planar orientation, these also have sp2 hybridized orbitals. So let me see if I can go to the, I mean, I could draw this out, but I believe you can draw this out just as well. If it's confusing, shout out. But this is hybridized, and that part I think you can clearly figure out because of it, all the steps I've just gone through. But this oxygen, in fact, has a trigonal planar conformation as well. It is hybridized as well to get the perfect angle and the perfect overlap. And also because of this double bond is the unhybridized p orbital, just like the example I just worked out. So you can have hybridization with an end atom with unshared pairs. And all 3 create this hybridized system. Okay, acetylene, you have a triple bond. So I'll start with drawing it, but I'm not going to try to draw a triple bond because I'm not that good of an artist. At that point, I will come back to this slide. So acetylene, also called ethine, acetylene is the common name. It's acetyl. So it's the carbon has a triple bond and one H on each end. So the AXC of each of these carbons is the same. So for this carbon, it's an AX2. There are no unshared pairs. That is the electron group of 2. This is linear. That is the electron group arrangement. And it has to be the shape. That's the only option. So that means my SP has to equal 2. So I have S. You always start with an S. And then what's next? I need 2. 1 plus 1. So it's just SP. So carbon again is 1s2, 2s2, 2p2. So I'm not going to bring in the 1s, but my 2s, my 2p, there's my s, there's my p. Remember, you always have 3. The ground state of carbon is this. I need an sp, I need 2 hybrid orbitals that are going to involve the s orbital and the p orbital. And I'm going to fill it with 2 electrons. This is from the carbon. I still have 2 p orbitals left. So that's left. And you know, you can actually, let's say, go back and for clarity purpose, let's try that again. For clarity purpose, because we're going to need these two. So to make the hybridized, let's say we use these, and these 2 electrons. Don't get too worried about what electron went where. Just make sure you account for 2, you have 2 left over, you have 2 p orbitals left over. That's more important. You use one of them in the sp, you have 2 left over. So I draw my carbon. Here's my sp, such as it is, and that's a sigma. And then there is also, because we have 2 of them, and the other one is going to the hydrogen, which is just the 1s. The hydrogen is not hybridized. So this is an sp, and this is a sigma. And we've got the same thing going over on this side. It's with the 1s of the hydrogen. This is an sp, and this is a sigma. Sigma, sigma, sigma. All right. But we now have a triple bond. So I told you there are 2 p orbitals left on each of the carbons. So here's one. We'll call it py. And it has sharing. So there's a double bond. The other one is coming out of the plane and behind. So use your imagination because we know my art skills. And this overlap is in front of and behind. That is my triple bond. So it's the 2 leftover p orbitals for carbon that were not involved in the hybridization are involved with the double and the triple bond, 2 pi bonds with the other carbon. They overlap, well, they overlap, but they don't overlap the way a sigma bond does. They overlap by parallel association. The electrons create, they share above and below with these parallel p bonds, p orbitals. So let's go back to the picture, which I'm sure is much prettier than my drawing. Not nearly as much fun, right? So here are your hybridized orbitals. There's your hydrogen. It is not hybridized. It's just a 1s. There's the py and the p. Okay, they're calling this a px. It doesn't matter which one you call it as long as they're parallel. And here's that overlap. with the PY. So that's one pi bond. And then here's the other one in front of and behind. So if you are asked how many bonds, if you're asked how many bonds are between the carbon-carbon, you have 3, you have 1 sigma, 2 pi. If you are asked how many bonds in the entire molecule, you have 5, you have 3 sigma, you have 2 pi. And if you are asked what are the types of bonds, you have 3 sp hybridized bonds, oh, okay. You have 3 sp, but it's 2 are associated with this carbon and 2 are associated with this carbon because the hybridization is for each central atom. So this is an sp, this is an sp. You can have different hybridizations. If this had a completely different molecular structure of connections at the end of it, you can have an sp on this end and let's say an sp2 on this end. So it's per central carbon, just like the Vesper is per central or central atom. In this case, though, we have this is an sp, this is an sp, and this is an sp, because this sp goes with this carbon, this one goes with this carbon, and this one is shared. So you would say you have 3 sp hybridized orbitals and 2, you could say 2 p overlap if I ask what kind, 2 p orbital bonds. There's all different kinds of ways to describe these. Okay. Nitrogen, N2, you have a double bond, and so, oh, I'm sorry, you have a triple bond, excuse me. 2 is a diatomic. You have 2 atoms, but it's a triple bond. And so you have the sigma and you have the 2 pi bonds from the p orbitals overlapped. The nitrogen on the end, the unshared pair, when you draw the Lewis of this, you have an unshared pair, is not involved in anything. So it's just a normal orbital. We're not going to worry about that. I think. Yeah, 1 sigma, sp, sp, yeah. Okay. Yeah. Go back and see what else is here. All right, so here's an example. How many sigma and pi bonds are there in this molecule, and what is the hybridization around the carbon? All right, well, each carbon has 3 connections. Each carbon is an AX3. They're all the same. AX3. Central, 3 connections. So that is an electron group arrangement of 3, which is trigonal planar. Each one of these is trigonal planar. And so you need an sp orientation that equals 3. So it's an S, 2 p's, sp2. So we know it's got to be either C or D. All right, how many sigma and pi bonds are there? There are 1, 2, 3, 4, 5, 6, 7, 8, 9 sigmas, because you always start with the single bonds. And how many pi bonds are there? There's 1 here and 1 here. So the answer is C. 9 sigmas, 2 pi's, and it's each carbon is sp2. So there's only 1 sigma bond, right? And there are 2 pi bonds. And so right there, that has to be A. And it's an sp hybridization. So, you know, you can just follow the normal routine. You might get that in Alex or something. Just a quick picture of, again, what hybridization looks like. Remember, hybridization creates, that's resonance. Okay, correction. This isn't hybridization, this is resonance. But when you have, so this is just a side thing. When you have P bonds, this is benzene, and you have resonance, and you have P bonds all aligned with each other like this, that can all share, they do. And in fact, this is an example where we show this as a resonance because this is in fact what's happening, is the electrons are sharing equally between all of these p orbitals, but we have no way to draw that. So this is an example of where we draw the double bonds shifting here and then here. But in fact, this is what, and this is benzene, and it's extremely stable because of this complete sharing. All right. I want to play that video. Now that you've seen all of this, it will make more sense because it's a lot of fun. The guy's funny. Here it is. And I think it does a really good job of explaining. Let me find it here. Of explaining hybridization. He goes through the steps one by one. So let's pay attention to his comments.
When I taught this a few years ago, a child spontaneously burst out crying halfway through with the horror of it all. All I could think of is delta G must be negative then.
Okay, I'm going to, hang on, I'm going to restart it with the captions.
When I taught this a few years ago, a child spontaneously burst out crying halfway through with the horror of it all. All I could think of is delta G must be negative then. Okay, so we'll start with carbon. That's the one they want to talk about. Electron configuration of, electron arrangement of 2, 4. And since we're doing higher level, let's do the whole SPDF business. So we've got 1s2, couple of electrons in there, and 2s2, couple more in that orbital, and in the 2p, well, we've got 2 electrons left, and so we're going to have 1 in the x and 1 in the y. So just like a liger is a hybrid of a lion and a tiger, and a z-donk is a hybrid of a zebra and a donkey, we are going to be looking at these orbitals mixing up and hybridizing together. So I'm going to take the 2s and those 3 2p orbitals, and they're going to blend themselves together, hybridize. I had the 4 electrons, I need to put those in as well. Spread them out according to Hund, Aufbau, and Pauli, whichever one of those laws applies to each box. Now this orbital is a hybrid orbital. It has energy between the 2 places it came from. So it's above the 2s but below the 2p. And it is known as the sp3. What was it made from? An s and 3 p's. So it's called sp3. That's your first hybrid orbital. Now what does it look like? Well, the s was spherical, the p was propeller. So when they come together, they kind of look like that asymmetrical, weird-looking thing. And if I had 4 of these, as indeed I do, because there's 4 orbitals, 4 electrons in, it's going to take up a tetrahedral arrangement. And now I've drawn the tetrahedron in 3D. So looking at the classic methane molecule, the carbon's already ready for the tetrahedron. And the hydrogen, when it comes in, is going to drop an electron into each of those orbitals, pairing up those electrons. And there's methane. Now, the sp3 orbital, all the orbitals are the same energy, and so that means the bonds are all going to be the same, length and strength. And they're called sigma bonds. So these are sigma bonds. Are you crying yet? No. Okay, so let's look at the next hybridization you need to know. So we're not going to mix 4 orbitals together. We're just going to mix these 3 here. So let me take the 2s over, 2pz and the 2py. Okay, so I've got 3 boxes now. And again, this needs to be filled with those 3 electrons that were just floating around there now. So 1 in each box. Put everything that we've just hybridized together, spin it around, and that makes an sp2 hybrid orbital, because you made it with 1s and 2p's. And again, These are sigma bonds that they're going to produce. And the P is going to produce a pi bond, P for pi. So let's look at H2CO. It's methanol. The carbon in green in the middle. Well, the hydrogen, when it comes along, is going to pair up its one electron. Another hydrogen is going to pair up another electron. It's making a second sigma bond. Now I'm going to stick the oxygen in. You just draw out the Lewis structure, put the dots in. It's in group 6, so it needs 6 dots. And so now we're going to pair up these electrons. So the orange ones come from oxygen, the green ones from carbon. Okay, so now we've got a third sigma bond there. And this oxygen still has an unpaired electron, and so does the carbon. And so that's in the p orbital. That's in the p orbital for both of them. So when those electrons pair up, that second bond is going to be the pi bond. So 3 sigmas, and in that double bond, one of them is going to be a pi. Now, do you remember what a pi bond looks like? Well, it's 2 propellers. Let me just draw out a couple of those. And they have overlap at the top and the bottom. And the p orbitals are parallel to the internuclear axis, of course. Tears yet? No? Okay, let's do the final hybridization. I've taken the 2s and the 2pz, same old things. Made a hybrid orbital of energy between 2 places it came from. Hydrogen cyanide is a good example for this one. So carbon in the middle, put the first hydrogen on, that's going to give me a sigma bond. Let's put the nitrogen in. Now the nitrogen's in group 5, so it needs 3 more electrons. It's going to get... So that's kind of going to be propellery, it's going to be pi, p propeller pi. And there's that final lone pair. So the triple bond has sigma and 2 pi's. Wow. I put this off for 2.5 years, this video. Tell me if it was worth it.
Okay, and that is sigma and pi bonding. Have fun.